In this video, we discuss arc length. In the previous chapter, we learned some applications of integration. For example, we learned how to find areas and volumes using integration. In some applications, it's useful to find the length of a curve. So in this video, we're gonna develop an integral formula to find the length of an arc of a curve. The idea is simple. So if you have a curve C and you want to approximate this length, you can determine the starting point and the end point, connect them with a straight line of length L, and you say that L is an approximation of C. If you want to get a better approximation, you may add more points. So here we graph two line segments of lengths L1 and L2, and we find that L1 plus L2 is a better approximation of the length of the curve C. If we add more points, we get a better approximation than the previous cases. So let's add 3 points. Between P1 and P5 we have 3 points, so let's graph these line segments. We find that this length, the sum of the length of these line segments is better approximation to the curve C. This is the idea. Now we use this idea to find a formula for the arc length. So if we have a function defined on AB, a curve C of a function that's defined from A to B, and we want to derive the formula for the length of that curve C, we may divide the interval A, B into subintervals. So let's use x node, x1, x2, and here xi minus 1, xi up to xn. These are subintervals of the original interval AB. The length of each subinterval is the same. It's delta x. Now the corresponding points on Y are P node, P1, P2, here Pi minus 1, Pi up to Pn. But these widths are not equal. For example, this is delta y1, this is delta y2, and so on. And later we'll use delta yi to denote these lengths because these vary. Now we connect these points with straight lines to get some approximation of C. So if f is continuous on AB, we can approximate the length of this curve by dividing the interval AB into n subintervals with endpoints x1 up to xn, and then we find the corresponding points P0 to Pn, and after that we draw line segments and we find the lengths of these line segments. The sum of these lengths of line segments is an approximation of C, but we want to get an exact value of that length. Now let's denote by L the length of the curve C. Now this length gives a better approximation as n gets larger and larger. So L can be approximated by the sum from I1 to n of pi minus 1 pi. This is the distance between any two successive endpoints of a line segment. Now, as if we want to get exact value, not approximate value, if we want to get exact value, we use limit. As n goes to infinity, we let number of points in the partition goes to infinity, and that gives us the exact value of the arc length. Now, what is the distance between pi and pi minus 1? If we have this part of line segment, this point here is xi minus 1 pi minus 1, and this point here is xi pi. This is the line segment that connect these 2 points. We want to find the length of pi minus 1 pi. The length of this is the distance in the plane. So the distance is xi minus 1 squared plus pi minus 1 squared. But we know that xi minus 1 is delta x. So this is delta x squared plus pi minus 1 is delta yi. So we notice that delta x is a fixed width, but delta yi varies. Now we can apply the mean value theorem here. This theorem says that if f is continuous on the interval AB, then there exists some point xi star in the interval, open interval. Let's use the interval xi minus 1 here. Xi minus 1 xi such that the derivative of the function at this point is the slope of the line that connects those two the points xi f of xi xi minus 1 f of xi minus 1 and xi f xi. So if we have this graph here, if we look at our graph, we can find some point here xi star where the derivative is the slope of the tangent line here. As you can see, the slope of this tangent line is the same as the slope of the line segment connecting pi minus 1 to pi. This is what the mean value theorem says. But we know that xi minus 1 is delta x, and fxi minus fxi minus 1, that's delta yi. Now we solve for delta yi. This gives us f prime xi star times delta x. Now we back to the formula here. We have square root delta x squared plus delta y I. Delta yi is delta x f prime xi star all squared. Now this is square root delta x squared plus delta x squared times f prime xi star squared. Now since delta x is greater than 0, we can first take this delta x squared as a common factor, and then we take the square root of this. So delta x squared is common factor here, 1 plus f prime xi star squared, and then the square root of, I should write this here. Now we need delta x to be greater than 0. So the square root of delta x squared is just delta x times square root of 1 plus alpha prime xi star squared. Now L, we want to get exact value, so for the arc length. So L is limit as n goes to infinity of the sum from I1 to n of pi minus 1 pi, but this is equal to this. So this is limit as n goes to infinity, sum of I minus 1 from I minus 1 to n, from I equals 1 to n, of delta x times square root 1 plus alpha prime xi star squared. Now, since this is a continuous function, limit of the sum is the integral. So this is the integral from a to b of square root 1 plus alpha prime x squared. We don't need the index here because we don't have sum, and delta x, we replace it with dx in the integral. So this formula gives us the arc length of a curve. You may write it as y prime squared. Instead of writing alpha prime, you may use y prime or dy over dx. Okay, now let's take some examples, since this is the formula that gives us the length of the curve y equals f of x on the interval ab. The condition here is alpha prime is continuous on the interval ab. Now let's do some examples. The first example here, we want to find the arc length of the curve y equals 2x minus 5, where x is between -2 from -2 to 3. So the length is the integral from -2 to 3 square root 1 plus y prime squared dx. Now we find y prime. Y prime is derivative of this is 2. So L is the integral from -2 to 3 square root 1 plus 2 squared dx, and this is the integral from -2 to 3 square root 5 dx. Now the integral of this constant is square root 5 times 3 minus -2. This gives us 5 square root 5. This is the arc length. Let's do another problem. Here the function is y equals 4 plus 2x to 3 halves, and x is defined, x is from 0 to 1. So the length L, the arc length, is the integral from 0 to 1 square root of 1 plus y prime squared dx. We need to find y prime. What is y prime? Y prime is derivative of this. It's 2 times 3 halves x to 3 halves minus 1. This gives us 3x to the power 1 half, or we can write it using square root notation as 3 square root x. So L is the integral from 0 to 1 square root 1 plus 3 square root x squared dx. And this is the integral from 0 to 1 square root 1 plus, now 3 square root x all squared is 9x dx. Now the problem is integration problem, how to integrate this function. If we look at the expression inside the square root, 1 plus 9x, this expression is algebraic, raised to power 1 half, because square root means power 1 half. So we can use the substitution method. U equals 1 plus 9x, then du is 9 dx, then we solve for dx, du over 9. but we need to change the limits of the integral 0 and 1. So when x equals 0, u equals 1 plus 9 times 0, and that's equal to 1. When x equals 1, then u equals 1 plus 9 times 1, and that's 10. So the integral becomes the integral from 1 to 10 of u to 1/2, or square root u, times du over 9. That's dx. We can pull this out, the integral, and then we integrate. So this is 1/9 u to 3/2 over 3/2 from 1 to 10, but we can flip this. 1 over 9, 2/3 u to 3/2 from 1 to 10. It's 2 over 27 of 10 to power 3/2 minus 1 to power 3/2. Now 10 to power 3/2 is 10 cubed under square root. And this is square root of 1000. This is square root of 100 times 10, and that's 10 square root 10. So this is 2 over 27, 10 square root 10 minus 1. Let's do another problem. Here we have y is a natural log function. So we want to find the derivative of this function. What is derivative of natural log? If we have natural log of f of x, then the derivative is the derivative of the inner function over the inner function. For example, ln x squared, the derivative is 2x over x squared, which is 2 over x. Okay. Similarly here, derivative of the inner function is derivative of secant. Derivative of secant is secant tan over the original, the inner function, secant x, and then we simplify to get y prime equals tan x. So the arc length is the integral from 0 to pi over 4 of square root 1 plus y prime squared, which is tan squared x dx. But we know that this is equal to secant squared x because this is an identity. So from 0 to pi over 4 square root secant squared x dx. And secant x is positive in the first quadrant, so we can cancel square with square root. So we get secant x dx. Now, but what is the integral of secant? There is a formula for the integral of secant. The integral of secant is ln of absolute value secant x plus tan x. And now we substitute 0 and pi over 4. So we get ln secant pi over 4 plus tan pi over 4 minus ln of secant 0 plus tan 0. What is secant pi over 4? Secant is 1 over cosine pi over 4, and that's 1 over square root 2 over 2. Flip it, you get 2 over square root 2. Then we rationalize the denominator to get 2 square root 2 over 2, and that's square root 2. So ln of square root 2 plus, what is tan pi over 4? Tan pi over 4 is 1, minus ln, what is secant 0? Secant 0 is 1 over cosine 0, and that's equal to 1. Plus, what is tan of 0? Tan of 0 is 0. So we get ln of square root 2 plus 1 minus ln of 1. Ln of 1 is 0. So the answer is ln square root 2 plus 1. Now, sometimes it's useful to find a function that measures the arc length from a particular starting point to any point on the curve. So the formula in this case is s of x is equal to the integral from a to x. As you can see, the upper limit of the integral is a variable, times square root 1 plus f prime of t squared dt. We change the variable here to t, just to not to have two meanings of x, the same variable. So here we apply similar technique, but the only difference is that the upper limit of the integral is a variable, so we expect to get a function of x after finding this. We don't get in general constant, but we get a function of x. So we find the derivative of the function y, so it's 2 times 3 halves x to 3 halves minus 1, and that's 3x to 1 half, 3 square root x. Now the integral, the s of x is the integral from a. A is the x value here. So we use the number 4 here to x square root 1 plus f prime. F prime is 3 square root x squared dt. We change x to t inside the integral. So this gives us the integral from 4 to x square root 1 plus 3t. 3 squared is 9. Square root t is t dt. And then we integrate this function. So we use the substitution method as we did before. So this is u equals 1 plus 9t. Then du is 9 dt. So dt is du over 9. And then we need to change the limits of the integral. So x, when t is equal to 4, then u equals 1 plus 9 times 4, and that's 37. When t is equal to x, then u equals 1 plus 9x. So the integral becomes the integral from 37 to 1 plus 9x of u to 1 half dt is du over 9, that's 1/9, u to 3 halves over 3 halves. We flip the denominator. We already integrated from 37 to 1 plus 9x, so we need to substitute them here. So 1 times 2, 2, 3 times 9 is 27. We have 1 plus 9x raised to the power 3 halves after substituting this here, minus we substitute the 37. We get 37 to the power 3 halves. As you can see here, this is a function of x. We got the arc length as a function of x. Let's do this example. We want to find the arc length function of the curve. In this case, the curve is y equals x squared minus 1/8 ln x, and the starting point is 1, 1. So the s of x is the integral from 1 to, because this is the value of x, this is the value of y, so we integrate on x. So we start from 1 to x, square root 1 plus y prime squared dx. But it's better to change this into t inside the integral. Now we find the derivative of y. The derivative of y is 2x minus 1/8. What is the derivative of natural log? If we have natural log, as we did before, of x or f of x, then the derivative is f prime over f. So here, what is derivative of natural log of x? It's 1 over x. Now we substitute this here. We get the integral from 1 to x, square root 1 plus 2x minus 1 over 8x squared, but we change it into t, change every x inside the integral into t. So this is the integral from 1 to x, square root 1 plus. Now we apply this formula. A minus b squared is a squared minus 2ab plus b squared. So here we expand this to get 4t squared minus 1/2 plus 1 over 64 t squared. And then dt, then we add these two, 1 to x square root 4t squared plus 1/2, because we have 1 minus 1/2 is plus 1/2, plus 1 over 64 t squared dt. Now if we look at this expression inside the square root, this is a complete square. And since it's complete square, we can write it this way. We can write it as parentheses raised to power 2. We bring the 2 from power. It becomes from power of the position over t. I mean, it was a power of t. It becomes a power of the whole expression. Now, completing the square, what is square root of 4t squared? It's 2t. What is the square root of the last term? 1 over 8t. What is the sign of the middle term? It's plus. Now, since this is positive on this interval from 1 to x, we can cancel square with the square root. So we get the integral from 1 to x square root 2t plus 1 over 8t dt. Sorry, we don't have square root because we canceled it with the square. So we integrate this. This is the integral here is, what is the integral of 2t? It's 2t squared over 2 plus 1/8. What is the integral of 1 over t? It's ln t from 1 to x. Now we substitute x. We get x squared plus 1/8 ln x minus, we substitute 1, we get 1 plus 1/8 ln 1, but ln 1 is 0, so we get x squared plus 1/8 ln x minus 1. And as you can see, we got a function of x that represents the arc length of the curve y equals x squared minus 1/8 ln x, taking 1, 1 as a starting point.